Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, everybody, thanks for coming to the MSR Colloquium. Today we're going to have Itai Ashlagi talk to us about unbalanced random matching markets, the Stark effect of competition. Itai is at Sloan currently, so right down the street, works a lot on matching markets, has done some great things with kidney exchange, even went to the Nobel Prize ceremony with Al Roth. And he's going to be at Stanford next year, so you should take advantage of this opportunity to talk to him.
Great. Thanks a lot for inviting me. This is joint work with Yash Kanoria and Jacob Leshno, who probably lots of you know. They were here postdocs. Actually, this work was done when there were postdocs here. So let me just tell you a little bit about market design that this work is a little bit part of. So in market design, we think about how to allocate resources among agents who are self-interested. And if we have all the data that we want, we can just optimize. But sometimes the market has the information. So agents are holding the information. If we just ask them for this information, they might be worried about what are they going to do with this information. And that's where we think about how to organize a marketplace. So we think about optimization with incentive constraints. And some markets are markets where the prices do a lot of the work, but some markets are not. And what I'm going to talk today about is those kind of markets that it's not just prices that do the work. And I'm going to look at a market, a two-sided matching market, a very classical model by Gale and Shapley from '62, where there's agents who have preferences, and the preferences think about there's rank order list of who they want to match to on the other side of the market. So each agent has preferences of agents from the other side. And there's no transfers in this market. And stable matchings, which is what Gale and Shapley introduced, can be considered as equilibrium outcomes in those markets. And this model was adopted, first of all, literally directly in centralized clearinghouses, for example, in the National Residency Matching Program, in school choice problems, and so forth. And also adopted in analyzing decentralized matching markets, like online dating, labor markets, college admissions, and so forth. In this work, we're going to try to ask or characterize what do stable outcomes look like. So let me give you a little bit of background. So first of all, a matching is basically every agent can be matched to at most one person from the other side. And it's said to be stable if I'm going to adopt here the notion of Gale and Shapley. There's one side there's men, and one side there's women. So a matching is stable if no man and woman want to leave their matches and go together. So if you got your third choice, it means your first or second choice are assigned or matched to someone they like better than you. OK, so that's a stable match. And Knuth showed this nice structure of stable matching that has this lattice structure. And there's one that is called the men-optimal stable matching, that men prefer it. Every man prefers it over any other stable match. And women like it the least. And there's one that is woman-optimal stable matching that women like the most and men like the least. And they also introduced a very natural algorithm, the deferred acceptance algorithm, which I'll describe later on in the talk, that computes one of those optimal matches. One version is the woman proposing deferred acceptance, which computes the woman optimal stable matching. Okay. So just to give an example, so we're all in the same page of how this model looks like. Maybe there's a few men and a few women, and these are the rank order list, who man A wants to be matched to, 1, 2, 3, 4, and so forth. And now I can ask if a matching, for example, here A is matched to 3, B to 2, is that a stable match? In this case, it's not a stable match because A can simply block with 1 or with 2 because 1 is not matched. He's happy to match to A, and A prefers him. Or with 2, because 2 is matched to B, which is his least preferred, and he's happy to match to A, and A is happy to match to 2 instead of 3. So this is not stable. Here's a matching that is stable. In this case, every man gets his first choice. Here's another stable matching that every woman gets her first choice. Clearly, those are stable because if everybody gets their first choice on one side, there's no blocking pair. Okay? So you see, this is 2 examples where there's one best for the women, one is best for the men. It's not always the case that there's a matching that everybody gets his first choice, of course. Okay. So here's a long list, and maybe there's more by now, of clearinghouses that are using, basically they're running centralized marketplaces. They're asking for rank order lists from the participants in those markets. So for example, take the National Residency Matching Program in the US. They're asking doctors and programs for their rank order list after their interviews, who they want to match to. And after everybody submits their preferences, they find a stable match and output that match. Okay, this is where you're going to work. And so there's lots of those, and there's evidence that those centralized markets that are using stable mechanisms that output stable matchings are working well. And there's some documented evidence for centralized markets that when they don't look for stable matchings, they fail because things like unraveling start to happen and so forth. But there's some evidence for that. But so there's this long list of places, all kinds of, you see, medical programs, also school choice and so forth, that are using those kind of mechanisms. And they work, some of them, for many, many years. And the theory doesn't explain completely still why those centralized mechanisms are working so well. So if you look at a theorem by Roth from '82, it says that no clearinghouse that finds a stable matching is actually strategy proof. That means that you can always find instances of preferences that someone will want to manipulate or misreport his preferences and might possibly get something better. Okay, so you cannot organize it that it will always be safe to report your true preferences. So that's
success.
What is it?
The notion of success. Do people measure? Do people know if people usually say the truth?
So why are those success in the sense that why are they still going on? And another, I'm not measuring exactly, giving a precise measure, but another thing can be, are we finding matches with respect to the true preferences? Are stable with respect to the true preferences or just to the submitted preferences? So if people are still misreporting their preferences, maybe we're not doing the right thing.
Do you consider the medical profession in general successful? Like, do you think medicine in this country is organized in a successful way?
I don't.
Gone that way for many years.
Just the match itself, I would maybe consider successful. I don't know beyond that.
No, but your justification for the success was that it's showing up for a while.
No, so in terms of why is just the clearinghouse itself is not breaking. That's all I mean. Okay? Because there's markets that look for example, for assignments that try to maximize the number of people who get their first choice. Those kind of markets, there's some evidence that unravel. Okay? Just in terms of the assignment itself, why are those clearinghouses not changing their rules or stuff? And so, but there's this theorem by Demange, Gillen, Sotomayor from '87 that says that if you as an agent, you don't have multiple stable partners when you look at the set of stable matches, you have no reason to manipulate your preferences. So if you can show, for example, that almost everyone or everyone doesn't have multiple stable partners or unique stable matching, there's no reason to manipulate your preferences, and you can recommend people to report their true preferences.
What's the definition of a multiple stable?
Yeah.
So if you take the set of multiple stable partners, means if you take the set of stable matchings, and I look at you as an agent, maybe if you have more than one match in that set.
Okay.
If you match different people across different stable matches.
So in some sense, if if there is a unique stable matching, then this
everybody
is
has a,
triviality.
yes.
Because obviously a mechanism that outputs the unique matching
Yes.
is going to up the unique
Everybody
matching
has
no
exactly
matter
one.
what happens. Okay, and
But there could be that some people have and some people don't have a unique.
people that don't have.
Yes.
No, but it's not a triviality in that, like,
No,
they
the-
can
the-
manipulate their
The
preference.
result is not trivial, but
Even
no.
if there's a unique stable matching, it's not a triviality because they could manipulate their
Oh,
preferences.
manipulation is not trivial.
If it outputs a stable matching, it will output that unique matching no matter what you do.
No, but it could be that with respect to.
Okay.
Oh, this statement is far from trivial.
I see. So if there is a unique stable matching according to their own
True preferences, it doesn't mean that I cannot manipulate my preference.
I see. They might. Okay.
Yes. So they show that if the core or the set of stable matching is small, there's not much room for manipulation. Yes. You can only yes. Yeah. Okay. So in this paper, we'll provide some explanation, hopefully, that why stable matchings are unique, even though we have the structure of this lattice structure and so forth. Okay. So we're going to actually look at random matching markets. I'll define in a second exactly what I mean by that. But by randomness, we're going to the random world because giving characterization in the deterministic world is hard. We have already seen that there's multiplicity there. So we're going to have a set of n men and a set of n plus k women. Okay? And every man has a complete preference list. We're going to rank every woman, and every woman is going to rank every man. But those ranking are going to be drawn uniformly at random and IID. Okay, so I'm
In the environment where everything is along a single dimension of heterogeneity and everyone is like assortatively matched, then there's just a stable there's a unique stable matching.
Yes.
What
Okay, so
I mean, you can consider it, the model he's describing is on one extreme of like a spectrum of models. So on one end is this model by Becker where everyone has the same, like there's better women and worse women and better men and worse men.
Yes.
And then there's only one stable matching, which is the best man and the best woman, etc. Here, people have totally spread out preferences. So you might think there's a lot of matchings here.
So you're saving me a lot of motivation for this model. I want to say exactly that, so that if there's more correlation, we expect that the set of stable matchings is going to be small. If everybody agrees who's the best man out there, then the best man is just going to choose who he wants to match to, and so forth. Okay, so to some extent, we don't have a formal proof of this, but to some extent, uniform at random is one of the hardest cases, if not the worst case. To have, if we find a small core or small set of stable matching in this case, then we expect to see a small set of stable matchings even when more correlation is in the market.
In the examples you mentioned, do you know how many stable matchings there typically are or something?
In the what?
Like in the National Resident Matching Program each year.
So there's evidence that I'll mention this in a couple of slides, but there's evidence that there's very small, that most people have a unique stable partner. Yes.
So I guess one way to interpolate between the two things that the two models, U model and the fully ordered model, would be, for example, if every man or woman has a number, and then basically when you set your preferences for every, say, as a woman setting my preferences, for every man I would draw a Gaussian, say, with that number, the expectation that number, and then the sorted list is going to be. So is that a model that has been studied?
So that suppose there was a priori qualities plus some random shock, like you're saying. That's a model that hasn't been studied much, and what would be interesting? What's the relationship between the error or the shock and the qualities? Would be interesting.
If it's infinite shock, then you have this, and if it's zero shock, then you have the.
Exactly. Yes. Or the qualities are all the same.
Yeah, I mean, the nice thing about that model is that you quantify how severe your effects are. Because I mean, you get these very extreme results, and you get a very extreme opposite result in the perfect vertical case.
Yes.
And so, yeah.
So to some extent, this is kind of, if we find that this set of stable matchings is small here, then we're probably good in when there's more correlation. And the IID is just independent preferences is technically helping us here. So the goal, again, is to characterize typical outcomes in those markets, but when there's a little bit of competition. By competition, I mean we're making the market we're going to make the market imbalanced. So there's going to be a different number of women and men. So we're going to look at two questions. One is how many agents in this model have multiple stable partners? Okay, that's the question that will be interesting from a manipulation perspective, but also understanding how many stable matches are out there. But we're also going to ask how each side is going to do in stable matchings in terms of who they are ranked to. So if you take a matching, you can look at what is the average rank, how men are doing in those, how good our matched men are doing, and how good matched women are doing in that matching. Okay, so let's say and let's think about if you're matched to your top choice, that's rank number 1, your second choice 2, and so forth. So it's sort of a welfare kind of measure for each side. Okay, so Pitel, Knuth, Motwani, and Pitel, and there's other works, looked at exactly this model when there's a balanced market, n men and n women. And they showed, first of all, when the market grows large, the core is large, meaning that the fraction of in the sense that the fraction of agents that have multiple stable partners goes to 1. And they also saw that there's a big difference if you look at the woman optimal stable matching. There's a big difference if you're a woman or a man. On average, women are matched to their log n rank, and men are matched on average to their n by log n rank. Okay, so it really matters if you're designing a clearinghouse in this model, if you are looking for the woman optimal stable matching or the men optimal stable matching. Okay, so what we want to ask in this, what happens, for example, if you add just one woman to this model, and what is the average rank if you add one woman in the woman optimal stable matching, for example? Yes?
Sorry, it's a bit of a digression, but has anyone looked at matching that's in between these women and male optimal that maybe has a better balance than this log n versus n over log n? Like
in this model?
Yeah, in this model.
Like you said, there's
even Pitel, I think, looked in the. I think you can find something that on average everybody is doing square root, but I'm not sure. But I'll try to convince you that it's not so interesting. Yes.
Both questions.
Mathematically, it's interesting.
So in the lattice of stable matchings,
yes.
Are there any other interesting stable matchings other than the given optimal and the man optimal that people have been studying?
Between what?
So in the stable matching lattice,
yes.
So are there any other interesting stable matchings that people have been studying? Like, I mean, these two.
Between those two. So people did look at some median stable matchings too, because.
You can prove that they're basically unique, so it sort of doesn't matter.
So people try to offer the median maybe to organize clearinghouses looking for the median and so on. So how also women are going to do that? So here they're doing very well, but now I'm adding a woman, so women's situations can be worse. How much worse than log n can it be? Okay. So there is documented evidence that take some in clearinghouses and some people estimated preferences when looking at decentralized markets. So Roth and Pearson looked at the National Residency Matching Program at the data, and over there they found that basically almost everyone has a unique stable partner. Hicho, Tacho, and Ariely look at online dating, the estimated preferences, and then they check using the estimated preferences. What they do in practice, they really run the deferred acceptance to the men proposing, the woman proposing, and they see if they have a different match. And they also over there show that there's essentially a unique stable matching.
And is that the matching that the decentralized market finds?
So that's a good question. I'm not sure. That's a good question. I don't know. With the estimated preferences, they have run a simulated model. I don't know what they do afterwards with the data itself. It's hard to understand. Yeah. So motivated by this work, in this work, Roth and Pearson, in that model, basically nobody ranked the entire market. People just interviewed with us some number of people, number of programs over in October. And more motivated by this, Nicole and Muhammad Madian wrote a paper about this model, the balance model, when there's n agents on each side, n men and n women, and men are ranking only a constant number of people, a number of women. And you let the market grow, and in that model explained why we see small core in the national residency matching problem. Okay, and Kojima and Patak extended that model. One feature of this model that happens is that we are going to see a lot of agents that remain unmatched. Because if every man only ranks a small number of women, lots of women will not even be ranked. So to some extent, you can think about this as a special case of our model when there's a big imbalance in the market. There's lots more women than men. And when preferences are correlated, we say also that what we talked before, we expect the core to be smaller and smaller. There is some comparative statistics on adding men to the market, but seeing how bad the men are doing in a given stable matching, in the men optimal or in the women optimal, but not across stable matchings. Yes?
Before you leave this slide, I have to ask about the Indian marriage markets. So is there actually a centralized market for
No. These are decentralized markets, the estimated preferences. And this is an interesting thing because here, in order to check if there's multiplicity, they really needed to run the deferred acceptance. There's not like, here's the market, how good are men doing, how good are women doing, and so forth. So they had to run it. Yeah. OK.
Also, you're saying people are actually running the deferred acceptance.
Yes. Yes. Here. No. People are looking for women directly, I think, or being matched by.
Once you have the list, you run it. You run it in on a computer. You don't.
Yes.
You don't send people on dates. And,
yes. So one thing I think we'll hope to do here is that we can say something about the stable matchings without running the algorithm. So here's the summary of results before I show formally. When there are unequal number of men and women, even by one, the core is small in the sense that almost everybody is going to be matched to the same partner. And there's a small difference between the men optimal and women optimal. So the small core, despite the long complete preference list and despite uncorrelated preferences. And the second thing is that the short side, even if there's just one more woman, are going to do much, much better in terms of who they are ranked to. Now, this is going to, I argue that this, to some extent, is robust. But this is going to be less robust. If every man, even if they're on the short side, every man agrees on the ranking of women, women are essentially going to get a better ranking than men. Okay? But in our model, short side is doing much, much better. Okay, so our results suggest that real matching markets will have essentially a unique stable matching. So let me start with some simulation results with small markets before I show the theoretical results. So here there's fix the number of women to 40. And we simulate a different market for each, fix the number of men, and we simulate the market with this number of men. And this is the percentage of men that have multiple stable partners. Okay, when we simulate. And only when the market is balanced, there's about 60-something percent of men that have multiple stable partners. And when you go to 39 or 41, it already drops down to around 20% and quickly down to small numbers.
Does your paper suggest a reason why the distribution is perfectly symmetrical about the center cores?
No. I'm not sure it's perfectly symmetrical also. It's hard to, maybe it's hard to see here. It's close.
Surprisingly close.
Yes. Yeah, it's not completely, but it's close, yeah. So what about the men's average rank? How they rank their matched women. So this, remember, low rank is better. This is what happens in the men optimal stable matching. So they are doing better in that matching. And this is the woman optimal stable matching. If you add one woman, this is pretty much the predictions by Pitel. And if you add one man or drop one man, men are going to do worse in the women optimal stable matching and better in the men optimal stable matching. But if you complete the graph, you can see that the real difference between them is only when the market is balanced. Otherwise, it's basically the same. Okay? And life is really good for men in this when they are on the short side, in the sense that if you take the mechanism that is called random serial dictatorship, which means if you order the men randomly and let them choose one by one the best woman from the remaining women, and you look at the average rank they get, this is what they get. You see the green line here. So when men are on the short side in the stable matching, they're doing almost as if they ignore women's preferences, choosing with ignoring women's preferences.
Life is good for men.
What?
Life is good for men.
In this,
Especially in like senior homes.
Yeah, exactly.
So like the right side is completely. I mean,
But
how do you count the rank of an unmatched person?
how? No, so
And when you're averaging?
so women. This is only for match people. Actually.
Okay, among matched people.
This is what it's like in Florida.
Dangerous talk to give. This is good.
I should reverse it. Okay. Here, men are doing bad. Okay.
That's the case in our field. There are many more men than.
Okay, so first theorem is about the number of men that have multiple stable partners. So with high probability, if you have n men and n plus k women, and k can be any number larger than 1, only a vanishing fraction of men have multiple stable partners. Okay? So this has design and strategic implication. First of all, it doesn't matter if you run the men proposing deferred acceptance algorithm or the women proposing deferred acceptance algorithm. You can just find one stable matching. You always find the same thing. And it also has strategic implication. You can recommend agents to safely report their true preferences. Okay? Second theorem is about ranking. So here I'm just, So it's about rankings. This is the version when there's just n plus 1 women. In the paper, there's n plus k women. But here you see that with high probability in all stable matching, men are doing well because they're on the short side. They're getting matched at most to their log n rank. And women are getting in all stable matching n over log n rank. And the differences between those optimal stable matchings is very small. That's the second graph. So this is for any k. But what you need to take from this slide, don't parse this now, but it's basically that if the balance is larger and larger, men are doing better and better, and women are doing worse and worse. That's what it says. Okay, so the second theorem tells us that with high probability under all stable matchings, men who are on the short side are doing very, very well, and they're doing almost as much as they choose, ignoring women's preferences, and women are doing almost as getting randomly assigned. Okay, so here's a special case with another constant fraction of women, and in this case, men are getting really a random. Really choosing, they're getting the average of a constant rank, and women are really getting a random assignment. And in this model, it's not so hard to show this, because if I start ranking, I rank my first woman, second woman, and so forth, very quickly I'm going to find someone who's just not matched at all. Yes?
So in the national residency matching program, N is the number of doctors, N plus K is the number of, N plus K is the number of doctors, N is the number of hospitals.
And every hospital can take more than one doctor, right?
Yeah, so in the national residency matching program, programs can take more than one. Usually it's not many. We have extension to that case when the number of the number of seats in each program remains small. You can extend similar results. You're asking about high imbalance?
The moral lesson that we can take from this is some sense that this example of Knus et al. Of like this large core is very, very sensitive. You perturb it slightly and
Yes, so those markets, yes, that's a very knife-edge case.
But the total number of positions available is much smaller than the total number of doctors in the national business matching program.
If it equals, why would it equal? I don't know.
No, I mean, it's much smaller, right? The total number of positions available.
Okay, so how big the imbalance is. I don't have the numbers here on my mind, but
Your results shows like doctors randomly match to positions almost, and positions get the best doctor almost.
I think it's too complicated.
no, there's more correlation. There's more correlation in that market in terms of preferences, and so it's a different. I'm just arguing here.
some of the models, some of these solutions are probably, these results are probably sensitive to your random model, which is probably, the real model is probably more similar to the model where everyone has ranked lists.
So how good is every side doing is much more sensitive to correlation, but actually the small cores or the uniqueness is probably is robust. That's what. And maybe one way to think about this is let's focus on just the top programs on that submarket, and over there maybe there's more heterogeneity than in a.
So Itai, I'm just like a old-fashioned supply and demand guy. So, like, is one way to think about this that like there's essentially a vertical supply curve and a vertical demand curve, and so if you have them literally coincide on top of one another, then there's like basically any price can be supported by the market. And if you have them moving slightly away from each other, the intersection, goes down to 0 or up to infinity, more or less.
So
I know it's not quite that simplistic.
It's very close to that. In 1 or 2 slides, I'll give a little bit more intuition about. Well, it's not pricing theory, but yes, it is. I'll try to get. That's the next slide. Yeah. So think about. To give some intuition, think about first of a market that there is n buyers and n sellers, and every seller is selling exactly the same good, and every buyer wants exactly one good. Okay, this is a classical, probably in every micro textbook. Every price in this market is going to be a competitive price because fix the price to be 100, no seller wants to drop the price or raise the price. Okay, so but if you add one seller to the market, the only competitive price is 0. Because now one seller is not going to sell. He wants to drop the price by epsilon, and everybody drops the price quickly to 0. In this market, it's a little bit more complicated because first there's not identical. We have heterogeneity of preferences, and there's no prices. But what happens here is that you add a woman to the market. That woman is now creating an outside option, maybe not to all men, but some men will be happy to match to that woman over their current match. Those women that are matched to those men who prefer this outside option are now creating outside options or indirect outside options to other men in the market. Because if those men who like this extra woman will defect or deviate to that woman, some women will be free now who some men will want. So this is a chain of indirect outside options that ripples through the whole market and makes men much, much better. Okay, so this is roughly what's going on. Another intuition that there's a famous theorem, a well-known theorem in stable matching called the rural hospital theorem, that if you take a market, fix the preferences, and it's unbalanced, it's always going to be the same people who remain unmatched. This is called the rural hospital theorem. Okay, so it's going to be hard to find a matching. If men are on the short side now, it's going to be hard to find a matching that it's always the same woman. It's going to be hard to find a market that it's always the same woman who remains unmatched and make men's preferences bad at the same time. So they have to be really good. Otherwise, someone will want to defect to that woman. Okay? So here, the price went down immediately. Everybody prefers the seller, but here the men became better off through a chain of indirect outside options. Okay, so let me tell you a little bit about the proof. First of all, we use the following algorithm, which is, I'll describe more precisely in a minute. if we start with the men proposing deferred acceptance algorithm, which is an algorithm, a sequence of proposals that gets from men to women that finds the men optimal stable matching. And from there, we continue with in a very similar fashion to the women optimal stable matching. And we're going to count proposals on the way and track who is matched to who also. OK, so let me start with the men proposing deferred acceptance algorithm. So that's the first step. Remember, men are on the short side. So every man starts by proposing to his top choice. Women who get more than one proposal, they reject everybody but accept the most preferred man, most preferred proposal. Men who are rejected now, who are not matched, are going to their second choice and proposing to their second choice. So women are tentatively matched, who are tentatively matched maybe from the first round, maybe get another proposal, and they look at the cumulative number of proposals, and they always reject everybody except the best proposals so far, including previous ones. So and then it goes on. Always rejected men go on and propose to the next one, and women always keep the best one so far. This ends in our model, it ends that every man is going to be matched, because men are ranking just everyone. OK, and it finds the men optimal stable matching. OK? So this is the first stage. After this, we find the men optimal stable matching. We want to move to the woman optimal stable matching. So the way to do this is to take some women, and we want to see if she has a better stable partner. So we're going to pretend as if she didn't like actually the last proposal, the guy that she was matched to in the men optimal stable matching, and try to get maybe better proposals. So by rejecting a man, she might get even a better proposal in the future, which will lead her to get a better stable partner. Okay, so that's one way to manipulate your preferences if there's multiple stable partners in the market, is to truncate your list, maybe to force the lattice go up. Okay. So what we're going to do now is, for every woman, we're going to check if she has a better stable partner. And there's two things that can happen once she rejects her current man. She rejects her current man. She causes a chain of proposals that can go back to her with a better proposal so far, and that's a better stable partner for her. Or it can go to this extra woman who is not matched, and then means that she doesn't have a better proposal. Let me illustrate this. Okay? So we ran the men proposing deferred acceptance algorithm, and we found the men optimal stable matching. So every man is matched to his best partner, and every woman is matched to her worst partner, stable partner. So I want to see if woman 1 has a better stable partner than M1. So she rejects M1, and the algorithm continues as if it was the deferred acceptance algorithm. So man 1 goes down his list and proposes to the next woman. And maybe she accepts him, maybe not. Suppose she doesn't. He goes to the next woman. She doesn't want him, so over her current match. So man 1 goes on, and he finds W2, who prefers M1 over M2. So she rejects M2. He's tentatively assigned to W2. M2 goes and proposes down his list to the next woman he prefers. He finds W3 and rejects, and W3 prefers M2 over M3. So she rejects M3, and this goes on, and maybe now it goes back to W1. And let's say W1 prefers M3 over M1, who was her worst stable partner. This means that M3 is now a better stable partner for W1. Because all you can do now is implement this chain that you found, or the cycle that you found, and record this matching, and M3 is now a better stable partner. Yes?
Just to make sure I understand the algorithm, in the alternative case that W1 did not prefer M3 to M1, she would just reject M3.
M3, it will continue. M3 will continue to propose.
She's unmatched, and she prefers M3 to the prospect of remaining unmatched.
That's right.
In this phase of the algorithm,
continues. She rejects M3. He continues to propose until he finds someone who's willing to accept.
So this is like she insists on getting something better than M1.
Exactly. Yes.
Okay, but if she doesn't, then how does that?
If she doesn't, so let's see what happens. M3, by the way, it can still come back to her later on with M5 or something. Okay. So those three guys now all found a better stable partner because I could start the cycle, this thing I could have started from W2 or from W3. So I record this, and I want to see if W1 has even a better stable partner because we want to go to the woman optimal stable match. So she rejects M3. And he proposes down his list, maybe rejected, finds W4, and this goes on. Now W4 rejects M4, and so forth. And this maybe goes now to this extra woman in the market that is not matched. Okay, suppose there's just one extra woman, W bar. In this case, W1, we know, this is from the rural hospital theorem, that she doesn't have a better stable partner than M3. That's her best stable match. Okay, so this is because otherwise, because this one, when we know she cannot be matched in any stable partner, any stable matching. So we know now that not just W1, all those four women already found the best stable partner for them. Because we could have started from W4, we know where to go. W bar, by definition, does not have a better stable matching. She has to remain unmatched, and so. So the real thing in the algorithm is going to be to track the set of women that we found from them the best stable partner. So suppose those are the women that we already know we found from them the best stable partner. We continue with the next woman. So the next woman, let's say W8, she rejects M8, and M8 proposes, and maybe now one of the proposals goes to this set. If W4 prefers M8 over M4, we know exactly where this chain is going to go to. It's going to go to W bar. That means that W8 also is matched already to her best stable partner. Okay? So if this set is going to grow very large very quickly, let's say after the first chain already, then you're almost done. Okay? And that's the essence of what we do in the paper. Okay, and okay, so we add W8, and we continue like this until we find for every woman the best stable partner. Okay, so the first step is to analyze the men proposing deferred acceptance algorithm. And this is similar analysis to Pitel. And the second, again, the second phase is to track the set of women that we find for them the best stable men, and see that this set is growing very fast. Now, why is it growing very fast? Let me give you a little bit of intuition. So if there's lots of the market is very large, and preferences are random, if you start with a big imbalance, then by default the chain will go to one of those. Every chain will be what we call the terminal phase. Those chain will go to one of those women. But if the market is such that there's just one extra woman, then first of all, chains are expected to be long because preferences are random. So when does the chain end? The chain ends either when you go to this woman, to W bar, or you go back to the woman you started with. Okay, and every time, if I'm now here and I reach this man, there's probability 1 over n roughly that if I didn't make so many proposals, 1 over n that I go to this woman, 1 over n that I go to this woman. Okay, so the first chain already is going to be quite long. There's going to be internal cycles, so it's going to be actually around square root n length. But one thing we need to show is that the first chain is going to be very long, because it could be that the first chain is already going back to this woman, and then many women have multiple stable partners, and that's a concern. But that's not happening because this woman, when we're done with the men optimal stable matching, this woman already got many proposals, roughly log n proposal, and this woman didn't get any proposal. So if a chain goes back to this woman, there's still small chance that she will accept that proposal. And that's why the first chain is already going to be pretty long. OK.
Sorry,
Yes.
it'll be very long and will end at W bar? Is that part of what you're saying, or?
It's going to be very long and go to W bar. That's important, yes. Yeah. If this woman didn't get any proposal so far, it will be with probability half go to here or probability half go to here. But that's not true. With high probability, it will go here. Yeah. And after that phase, you already have square root n. The size set S has already square root n women. OK. Can we allow correlation in preferences? So the more correlation we have, we expect them to be a smaller core. And we mentioned this. Sometimes what is imbalance exactly is something we need to think about. You can look at special cases like there's 30 doctors, 40 medical programs, and every doctor prefers the top 20 programs over the bottom programs. In that market, there's still going to be a unique, or roughly unique stable matching because you find the stable matching only with the 30 doctors and 20 top programs, and then the remaining guys are matched to, the remaining doctors have to remain to the other programs. Yes?
In the cases you're looking at, are these tiered markets really that exceptional? That seems more the norm than the exception. You would have
This.
These tiered markets as opposed to a really clear short side.
So I guess probably the normal thing would be not even this complete tiered, but like there's probably going to be noise in between tiers. But in clear tiers, we can say follows from these results that there's going to be a unique stable matching.
In some sense, it's unique. You're saying it's almost like two different unbalanced. Like in the first market, there is like 30 doctors on 20 programs, and then in the second market, there are 20 programs on 10 remaining doctors.
Yes. Yes.
So the long side.
So it flips like the.
Yes. And I think it's interesting to analyze those kind of markets to understand better who we want to invite for interviews and things like that. So maybe I do have random preferences among those 20, and then random preferences among those 20. Understand better where are my potential matches. That's interesting. Right now, we just give reasoning why there's going to be a unique stable match. And OK. So what is a general balance condition is an interesting question for future research. Here's some simulations with correlation. In the paper, there's more simulation results with correlation. Here, one side is completely random. One side has preferences from a logistic distribution. There's beta is some coefficient. And so man M ranks women W, beta times W, with beta is some coefficient for correlation. And epsilon is from a Gumbel distribution. So if that goes back to what we talked before. So if beta is 0, we're back to our model. And if beta is high, there's almost perfect correlation so men agree on women's preferences. So what you see here, if you are, the more left you are, the more random the preferences are. So here, men are doing, the blue and the red are the rankings of men in the men optimal and women optimal. And here they're doing very well, but the more men agree on how good women are, the more women are doing better and better. Women are becoming more choosing than men are becoming more chosen. This is the random serial dictatorship. This is the percentage of multiple stable matchings. Here you see the percentages. For some reason, it's not monotone, which is maybe interesting, but it doesn't go to high numbers like 60 as before. It goes to around 5%. Okay? So we give a bunch of simulations in the paper that also show that really with different kinds of horizontal preferences and that show really that the balanced uniform case is really the knife edge case. Here's some more simulations with maybe some larger markets. So this is when it's balanced, and this is when it's it's indeed very close. Like it's almost symmetric. No, it's not completely symmetric. No, it is. Okay, so I'll conclude here. So we studied random unbalanced matching markets, and the real conclusion is that they're highly competitive, as if there were prizes out there. And we find essentially a unique stable matching, and the short side is highly favored in this market. Our results suggest that matching market has a small core, and that this means implications for clearinghouses that it's safe to report your true preferences, and it really doesn't matter how you organize on which stable matching to find. Maybe one more conclusion is we don't know much about optimal matching. So if we have some, let's say, in school choice, for example, we need sometimes to bus students, and we have some budget constraints, or we care about other objectives. We don't know about so much optimal matchings. But if we do constrain ourselves to stable matchings, then maybe the only focus is on choice menus, or what are the feasible stable matches, and not which stable matching to find. So yeah, I'll stop here.
Questions?
I think 2 slides back, you said an interesting open question was a general criterion for balance. Okay, it was more than a general balance. What does that question mean, or can you elaborate on it?
So I guess the fact that there's 50 men and 40 women doesn't mean that men are on the long side. You need to really start understanding the preferences. For example, in this case, doesn't mean the programs are on the long side. Really, it's the top programs are on the short side, and the bottom programs are on the long side. And if preferences are more involved, we don't really know. So I understand pretty much
So this isn't
the future question. I really want to.
It's a general rule of thumb for looking at the preferences and deciding which side effectively gets to choose. Is that?
So maybe I would write it different a bit now in the sense that where are my potential matches? So just in our model, we know that the short side can look at the top log n preferences. But when there's preferences are more involved, then who should I look at? Should I look at how many people from this tier, how many people from that tier? And what if tiers are even not exactly completely distinguished? What do I look at then? And so forth. Those kind of questions.
Let's thank the speaker. There's food outside.